Hi, so I'm going to go through an example problem here using the method of undetermined coefficients to solve this second order initial value problem. So we've got a second derivative linear and then our non-homogeneous function 2x plus 4. So just a linear term there. And then we have some actual initial conditions as well. Okay, so the homogeneous part I'm going to go through pretty fast so we can convert this into our characteristic polynomial. So the derivatives become the power, so r squared minus r minus 2 equals 0. And solve that using the quadratic formula. You'll notice that it works out pretty nicely here. So into integer values. So I get my two roots here. And remember, so this is the solution to the homogeneous problem. That's where we're pretending that the right-hand side is 0. And there's my homogeneous solution. So it's going to be the combination of e to the 2x, right? So this is from that roots of the polynomial and e to the minus x. And then these two coefficients, c1 and c2, will be determined by the initial conditions. However, I should not solve for those until I put the whole thing together. This is the general solution if the right-hand side was 0. We have not found the general solution to the non-homogeneous problem as of yet. We need to add in the particular solution first and then apply these to solve for C1 and C2. Okay, so for the particular solution, like I said, I'm going to use the method of undetermined coefficients, which is our kind of guess and check method. So we guess that yp of x is equal to this linear function ax plus b, and then I'm just going to plug that into my second order ODE. So you notice that, y double prime is 0 here, right? Second derivative of this with respect to x is 0, and so I don't need to worry about that. So this is 0 minus, and the first derivative just gives me a, so that's my minus y prime, minus 2 times, and then this is y, so this is y and y prime, equals my right-hand side 2x plus 4. And we're going to try to choose the a and b here so that we find a solution, because all we need is just the one solution. So what we do is, so I'm going to expand it out a bit, and then I'm going to match the coefficients. So I need the coefficients, anything that the a's and b's over here need to combine to give me 2 as a coefficient for x. So I'm setting minus 2ax, that's the only term that involves x, equal to 2x, which tells me right away, if I solve for a, that a is negative 1. And then the coefficients for x to the power 0, just the constants, would be, I get a minus 2b from here, and minus a, and that should be 4. b equals 4 plus a over negative 2. So b is minus 3/2. So this gives me my one solution that if I plug this in to this differential equation up here, I'll get 2x plus 4. So to make the general solution, then, we take our homogeneous solution and we add in that one particular solution. And now is when we can plug in these initial conditions and solve. So I want my solution. So the idea here, by the way, for a general solution is that for any initial conditions, they now live in this family. I can solve for the C1 and C2 to specify that particular solution that we want. In this case, I want a solution where y of 0 is equal to minus 8.5, and y prime of 0 is negative 9. So if I plug in y of 0, I get C1. So e to the 0 is 1, e to the 0 is 1, minus 3/2 equals, and then I think I already did some algebra over here. So that's minus 8.5. And then the second one, I have to take the derivative first, which is going to cancel. The minus 3/2 term will go away, and then minus 1 will come down in the chain rule, and 2 will come down here. So I get this, and then I'm going to plug in 0 for x, using that e to the 0 is still 1 for this term and this term. Minus 1 equals negative 9. All right, so I have my two linear equations to solve for C1 and C2. If I move those extra terms over, I get C1 plus C2 is negative 7. Negative C1 plus C2 equals, moving that over, minus 8. I could just straight up add these two equations together and the C1s will cancel. So I get 0, C1, 3, C2 equals negative 15. Divide through, C2 is negative 5. And then once you get one, the other's pretty easy. So I could just use this top equation. C1 is minus 7 minus C2 minus 7. Minus 5 is negative 7 plus 5, negative 2. Which gives me, finally, the solution to this initial value problem is here, right? So now I fill in C1 is negative 2, C2 is negative 5. And notice you can check this, right? So like you can always check that you found the right solution here. So y of 0 is minus 2 minus 5 minus 0 minus 3 halves. So that gives me my minus 8.5, which is what we have here, right? And then same thing, I could do the same thing with the derivative to check that. So that's always a good sanity check when you finish one of these kind of problems to make sure that you've really plugged in at the right stage. But as a lesson on this, make sure that when you're solving these non-homogeneous problems, you do everything. You find the full general solution, and then you apply the initial conditions to find those constants. If you do that early, then you'll end up with a wrong solution.